Alright, so let's begin our examination of feedback with a gain sensitivity analysis. And the way that we do a sensitivity analysis is by taking a derivative of one property with respect to another. So what we're looking at is we'd like our gain to not be very sensitive, so we want our feedback to reduce gain sensitivity. Alright, so we know that our closed loop gain, ACL, is equal to little a, the gain of our amplifier, divided by 1 plus little a times beta, the loop gain of our amplifier. So if we take the derivative of the closed loop gain with respect to the open loop gain, we would get the following quantity: 1 plus a times beta quantity minus a times beta divided by 1 plus a times beta quantity squared. And if we manipulate this, we see that this is equal to 1 over 1 plus a times beta quantity squared. So we can look at dA closed loop is equal to dA, the change in the open loop gain, divided by 1 plus A beta squared. So what we see is that changes in our open loop gain are reduced in impact by the feedback factor of the amplifier, or by the loop gain actually. Alright, we can also do this as a fractional change. So we could say, look at this as dACL divided by ACL. So what we're looking at is a fractional increase, is what the fractional increment in the change in closed loop gain is as we change the open loop gain. So if we make some substitutions, we know that dACL is equal to dA divided by 1 plus A beta quantity squared. And we know that ACL is equal to little a divided by 1 plus A beta. So this whole expression is equal to dA divided by A times 1 plus A times beta. So again, what we see is that we get a small fractional change in closed loop gain for a change in the open loop gain. And that's what we want to see. It's easy to make a very large open loop gain, but it's very difficult to make a very precise open loop gain. So we'd like to not have our circuit depend very much on the amplitude of the open loop gain. Alright, what we're going to start to look at now is what types of amplifiers can we make and what would the impedances be based on the type of feedback that we use. So first, let's look at what we would want for ideal current amplifiers, for instance. So let's say we want an ideal current amplifier. What do we want the impedances to be at the input and the output? So for a current amplifier, in order to avoid current divisions, at the input of the amplifier, we'd like the input resistance to be small. At the output of the amplifier, we're trying to output a current, and so we want our output to look like a current source. So remember, our ideal current source has a large impedance, so we'd like our output in this case to be large. So this is the opposite of our voltage amplifier. Remember, a voltage amplifier, we want the input to be large and the output to be small. In a current amplifier, it stands to reason that since current is the dual of voltage, we'd like the opposite conditions. Now remember, we don't just have to stop with current amplifier. We can also make what we call a transresistance amplifier. And in a transresistance amplifier, what we're going to get is a current to voltage amplifier. So input current input current, let me write that better. And we output a voltage. In other words, what we're looking at is V out divided by IN, which looks like a resistance, right? So in this case, we're going to input a current. We'd like our input impedance to be small to avoid a current division at the input. We'd like all of our current to flow through the input resistance of our amplifier. And our output resistance, we're trying to output a voltage, so again, we'd like this to be small to avoid a voltage division at the output. Now, in addition to a transresistance amplifier, we can also dream that we might have a transconductance amplifier. Of course, this is what a transistor does naturally. It converts a voltage to a current. So here we have an input voltage that leads to an output current. In other words, we get an I out over Vn. And in this case, we want the dual of the transresistance amplifier. Our input resistance should be large to avoid a voltage division at the input, and our output resistance should be small to avoid a current division at the output. So what we can come up with is a few general rules here. So in general, if we're sensing a current, we want a small resistance. If we're sensing a voltage, we want a large resistance. Think to what your ideal multimeter looks like. In your multimeter, when you're measuring a voltage, the impedance of the probe should be nearly infinite, or at least very, very large. And when you're measuring a current, you want the resistance of the probe to be very small. Same thing here. In our feedback loop, we'd like current sensing to be small resistive and voltage sensing to be large resistive. Now, when we're outputting a voltage, we want a small resistance, again to avoid voltage division at the output of the amplifier. And when we're outputting a current, we want a large resistance to avoid a current division at the output. Alright, so in the next part of the lesson we're going to learn how to identify the type of feedback that we're looking at and what types of amplifiers we might use that feedback for.